So previously we had this discussion of saturated fatty acids versus unsaturated fatty acids. We defined them. We said saturated fatty acids were fatty acids that had all single bonds throughout the molecule, and we said that unsaturated fatty acids are ones that had double bonds in the molecule. So that's your first trait of fatty acids that you should learn by now. Well, we said that with saturation or saturated fatty acids, the longer the chain, the melting point goes up. And then we looked at unsaturated, and it looked like as long as we increased the carbon chain, our melting point began to go down. But don't fall into that trap. And here's the reason. We need to take a look at what this structure basically is doing for us. So here's a fatty acid. This is a saturated fatty acid that we mentioned in a previous video, stearic acid. And we in general chemistry and in organic learned about these things called Vander Waals forces. Right? And these Vander Waals forces was a mixture of hydrogen bonding, and it was a mixture of dipole-dipole bonding, and it was a mixture of what we called London dispersion. And London dispersion is what we're going to focus on here. This is kind of going to be the most important one out of the bunch because this is what these molecules are going to be seeing. So what is London dispersion? This is random. That is what we said back in the day. It's a random force. So what you got to keep in mind, number one, is that these molecules, especially in this area of the structure, well, these molecules basically have no functional group. These molecules, they basically have no polarity that's associated with them. It's all carbon and hydrogen. It's nonpolar in nature. So nonpolar basically means no hydrogen bonding can happen in this area. It also means no dipole-dipole because this requires charges, and we don't really have charges here. But this is London dispersion, and we said that London dispersion, the electrons are in constant movement. And because the electrons are in constant movement at any random point in time, hint, why we wrote the word random down, we could get a lopsided molecule with electrons on this side temporarily, and when that begins to happen, we see a partial negative and a partial positive charge that happens to that piece of the molecule. So the electrons become lopsided, and the electrons rush onto one side of the boat, and the boat begins to tip back and forth. The same thing happens with stearic acid. The boat begins to tip, and we get some movement that happens. This is London dispersion. And London dispersion leads to intermolecular forces. And intermolecular forces lead to basically glue that holds the molecules together, which means a higher boiling point and a higher melting point. If we do something to disturb the London dispersion of the molecule, if we do something to basically get rid of some of the glue, then the molecule's melting point and boiling points begin to decrease. What is one of the things that we can do to prevent this glue from sticking the molecules together? Well, you see it right here. It's the double bonds. The double bonds disrupt the linear structure that these fatty acids begin to take on. And the more double bonds that you have, the less linear it is, which means it can't stack as well, which means the forces go down, which means the London dispersion goes down, which means the melting point and boiling points go down. And that's actually what you're seeing in the bottom half of this table. So the bottom half of this table, the first two are given because both of these have one double bond, and they're letting you know Just like from up above, if we increase the carbon chain, we do have an increase in melting point and boiling point as long as we're talking about the same number of double bonds here. So that's why they give you the example of 16 and the 18 carbons. They give you two examples. They only are differ in the number of carbons that they have in the chain because the number of double bonds are exactly the same. So they're letting you know again the melting point does increase if that happens, just like it happened up here. Longer carbons, more melting point. It goes up, up, up. Then at this 18 carbon chain, they're showing you two versions of 18 carbons. This one has one double bond, and this one has two double bonds. And look at what happens to the melting point when you throw in multiple double bonds. The melting point goes down. This molecule becomes less linear. If it's less linear, it can't overlap as well. If it can't overlap as well, it can't stay glued together as well. If it can't stay glued together as well, the melting point and boiling point go down. So this COOH, what we see is that the melting point decreases, and it's due to that extra double bond that's thrown into the mix. The same thing is going to happen here. We get 3 double bonds thrown in. It's still 18 carbons in total. Well, look at what happens to your melting point. Extra double bonds, extra kinks. Extra kinks means less glue to keep them together, and your melting point goes down. Then finally, the two examples down here at the bottom, notice they have the same number of carbons, 20 apiece. One of them, however, have 4 double bonds. The other one has 5 double bonds. The one that has 4 and 5 double bonds, they're letting you know that these melting points are about the same in this case. And the reason is because the molecule is so crooked at this point, you can't really get it any crookeder, if that's a word. So that's the example of how double bond characteristic affects melting point and boiling point of these fatty acids. The more double bonds you have, the lower the melting point will go. But there will be a stopping point, and sooner or later you're going to get to a point where you're going to look at these molecules and understand that these melting points and boiling points are not really going to be affected that much more if we throw in more double bonds or if we throw in more kinks into the system. So this table is given in the book. It's very important for you to understand the information that this table is trying to convey, and that is what they're trying to tell you. Up at the top, longer carbon chains increases melting points and boiling points. The same thing happens down at the bottom. The longer carbon chains, as long as it has the same number of bonds, double bonds at least, your melting points and boiling points increase. What changes the unsaturated fatty acids, though, is that the more double bonds that they have, the more crooked the molecule becomes, and the lower that melting point or boiling point will be. So that is what we call a fatty acid, and there's two different types of fatty acid, saturated and unsaturated. The same thing can happen basically to this slide. I mean, that's kind of what they're showing you here. So they're taking stearic acid, and stearic acid is a straight chain fatty acid. There's no kinks in it at all, and we see the COOH group here on the end. Oxygen, of course, are the red orbs. This melting point, T sub m, is 69 degrees. Well, this is an 18 carbon fatty acid. If I throw in a double bond to the mix, I get a kink. And that's what we're seeing here. This is a kink in the molecule. And it can't stack as well. And because of that, look at what happens to the melting point. It plummets. It goes from 69 to 13. And then in the next example, they've thrown in an extra kink into the picture. You get 2 double bonds here that are really close together. Well, the molecule was already crooked here, and the molecule becomes more crooked there, and we see a lower melting point because of that reason. Not as dramatic as the first one, but it's still much lower. It goes from 13 to -5. And then in this example, we see a molecule with 3 double bonds. It tells me that, 3 double bonds right there. So I see more curvature that happens in that molecule. And because that molecule is more curved, it doesn't stack as well as the others do. And because of that, the London dispersion forces, well, they're not as great. There's not as much glue there to hold the molecules together. And I go from a -5 here to a -11 there. Again, it's not as dramatic because the molecule in linoleic acid was already kind of crooked, and by throwing in a third bond, it does lower that melting point, but not as much as if I went from stearic directly to this. Then that would be a dramatic drop. But going from linoleic to this one is not a dramatic drop. The molecule, again, is already crooked in the beginning, so just because you bend it a little bit more, you'll see a change, but not that big of a change. Something else that I want you to pay attention to is the melting points and boiling points that are listed. If I look at stearic acid, the melting point is 69, which means you need to heat it up to 69 degrees before it melts. So what that basically means is that at room temperature, which is 20 to 25 degrees, stearic acid will be a solid. That's something that we've got to keep in mind as we begin to look at these melting points in these structures. Stearic acid is a solid, which basically means that saturated fatty acids tend to be solids in nature. And if I go back and take a look at this table, you will kind of see that already on the table. These saturated fatty acids, well, the lowest one that's listed on this table is a 44. That means you have to heat them up to 44 degrees before they melt, which means that they are a solid at room temperature. Room temperature is 20 degrees, 25. If this melting point is higher than 25 degrees, that means you have to heat it up in order for it to melt. However, down here below, the unsaturated fatty acids, look, the very first one, a 16 carbon chain. This 16 carbon chain was 63 degrees. It's going to be a solid until it hits 63 degrees. This 16 carbon chain, because of that one double bond, its melting point is 0. Which means that at room temperature, this is going to be a liquid. Well, that also means that this one's going to be a liquid. You have to heat this one up to 13 for it to melt. Well, room temperature is 2025. It's already hotter than the melting point. And that is why oleic and linoleic and linolenic and arachidonic are all liquids at room temperature. So keep in mind what melting point means. Never lose that piece of information and that common sense type of knowledge. So at room temperature 2025, do you have to heat the molecule up hotter to get it to melt? If so, then that means it is a solid at room temperature. Don't be surprised if you'll see that on some of the questions in the Mastering Chemistry. Don't be surprised if you see some of that in the quiz banks. Don't be surprised if you see some of that on the test. Is this fatty acid a solid or a liquid at room temp? And that's the way that you will answer those questions. Oh, well, oleic is 13 degrees. Room temperature, 2025. That means that hotter than 13 degrees, oleic acid melts, which means at room temperature, this thing is a liquid. So take that to the bank. You're going to see it again much later on.